All right, guys, thanks for taking the time to watch this short and last minute video. But I thought it'd be a really good idea just to send this through to everybody just to make sure that we've covered all bases, because I know that I haven't done this with my students and it's come up a couple of times in the practice exams. And I just want to make sure that everyone knows how to do it. Now, earlier in the term, we had to flick through the textbook, and from what I can understand, this isn't in our textbook, but it is definitely something that VCAR could ask us about. And so it's calculating the enthalpy change of a reaction, not by just looking at the data book, but by using the bond enthalpies. And so that's what you would need to do here. This question reads, calculate the enthalpy change of the following reaction, and they've given us methane combusting with oxygen. It's complete combustion because we're making carbon dioxide and water, and it's essentially asking us to determine what the delta H value is to make this a thermochemical equation. So how do we do that? So in page 9 of your data book, you have these two tables which outline the average bond enthalpies of single bonds. And so the way you would read this is, for example, if you're looking at a bond between carbon and chlorine, you would go over here in the table and you would read this, and it would be 324 kilojoules per mole for each of those bonds. And then if you were looking for a double bond, you would need to come to this table, or a triple bond, because there are triple bonds here too. And if you were looking for a oxygen to oxygen double bond, you'd be looking at this value here. So that's just a really quick one on how to read the table. And you'll notice that there are a couple of places to find each type of bond in this table. Like, for example, you could read carbon to hydrogen this way, which is 414, or you could read carbon to hydrogen this way, which is, again, 414. It's just the way the table is constructed. Don't get too confused by that. So to start off, it's extremely important that the equation that you're working with is balanced, because we need to work out how many of these bonds in total we are breaking in the reactants, and then we need to work out how many bonds in total we are forming in the products, work out the difference in energy, and that's going to be our enthalpy change for the reaction, or our delta H. So looking at those two tables in the data book, we will notice that we only have these 4 bonds present. So carbon to hydrogen in our reactant methane. We have oxygen to oxygen double bond in our oxygen molecules. Then in our products, we have carbon to oxygen double bonds in carbon dioxide. It's important to remember carbon dioxide is linear, so there are double bonds here. And then we have oxygen to hydrogen double bonds here. So what I've done is I've just made a quick list on those values. What you might do in an exam is just maybe put a little dot next to them. You don't need to go writing them out because you're going to waste a lot of time by writing this step out. However, you may want to write down what type of bonds you have. That's a really good thing to do. I would suggest writing them down. Just a quick list of those 4 bond types, just so you know what you're working with and you don't leave any out. Next, we need to add up how many of the bonds in the reactants are being broken, and then what energy value that's going to equate to. So here's a quick summary of what that looks like. So because we have 1 methane, we have 4 carbon to hydrogen bonds being broken. And so that's going to look like this: 4 times the value that's assigned to a carbon-hydrogen single bond, and that equates to 1,656 joules. So we leave that there. We then need to work out what other bonds do we have. We have 2 oxygen to oxygen double bonds. Now, why do we have 2? Obviously, there's only 1 of these bonds per molecule, but we have 2 oxygen molecules reacting for every 1 methane. It's really important that you get the mole ratios right here and that you include them in the calculations. You need to make sure you times them by the mole ratios. And so here we times 2 by 498 to get 996 kilojoules. And then we just add those 2 totals up to get the total energy that is being released through the breaking of the bonds in the reactants, which ends up being this number here, 2,652. That's the first step. Then we need to move on to working it out for the products. Here is a quick summary of that. We look at our carbon dioxide. We have 2 carbon to oxygen double bonds because there's only 1 molecule here. And so that ends up being 2 times 804, this number. Again, we need to make sure that we times the number of oxygen to hydrogen by 2. So we had 2 per molecule, but we're then timesing that again by 2, which means that we have a total of 4 of these bonds. Times that by the number, we get this. And so we have our 2 numbers that we're going to be working with for the reactants and the products. The last thing we need to do is use the equation, which is for delta H. And so we use the energy of the bonds broken and we subtract the energy of the bonds formed. And so, long story short, we take 2,652 and we minus 3,460, and we end up with this number, negative 808. And you might be thinking, why is it a negative number? Well, it's pretty intuitive because this is a combustion reaction. It's expected to be exothermic, and so we expect the energy value from the reactants going to the products to be a negative difference. It's going to be a decrease in the energy of the products compared to the reactants. So this is a true value. Now, if you look in the data book, you're going to find that this is not the value given for methane. It's not the molar enthalpy. However, this is going to be slightly different due to experimental data being used for the values for bond enthalpies and then also for molecular molar enthalpies. So don't stress that it is different. They will be different. And so this is the answer for this question. And so I could write up, if I wanted, delta H equals negative 808 joules per mole. So here's a quick summary of the steps. You need to make sure you write a balanced equation. It's very important that it's balanced. You can't do this question without balancing the equation first. Then you need to make sure you identify the delta H of all bonds present. So you get this from page 9 of the data book. Then calculate the total energy of the bonds broken in reactants and products. And then finally use your equation. So the delta H of the bonds broken in the reactants minus the bonds in the products. So I'm going to give you one more example that you can do in your own time. So this one here is a little bit more complex because you have to do one more step. So it says here, calculate the enthalpy change of the reaction for the complete combustion of ethanol in air. So this one's a bit nastier because they haven't given you the balanced equation. You need to do that first. Now remember, in our steps, that is the first step. So if it's done for you, fantastic. You just start from step 2. But here is a good example of where we need to start from step 1. So I'll leave this here for a second. I'll get you to work it out, pause the video, and then play when you're ready to see the solutions. Okay, so the first step here was balancing the equation. So you'll see here, ethanol reacts with 3 moles of oxygen and gives 2 moles of carbon dioxide and 3 moles of our H2O. Now, if I go to the solutions, you should be able to follow those through and see how they got to their answer. So if you have any questions, make sure you send me or Dr. Dooner an email, and all the best with your exam, guys. Big year leading up to this point, so smash it. See ya.